run out of disk. And share my screen. Share. Can everybody see my screen?
Gotcha.
I'm trying to see if I can maximize this other window. I seem to have lost my controls when I do that.
They're probably up at the top of your screen, and they'll only show up if you mouse over.
All right. I can resize the window. I believe I can.
Right.
Resize window. I have to do it from this side.
We have control from our side too, so I'm not sure there's anything you can do. I mean, this screen, we're seeing the slide.
Good.
It's nice and big.
All right. What I can't see is if someone is trying to come in. I'm not getting that message now. So hopefully it's okay. So welcome to the January 2022 Society meeting, encouraging and supporting members and general public in the study and practice of astronomy. And I believe I'm recording. Is it showing that the meeting is recording, Steve?
It is.
Yes.
Okay, good. The agenda is our feature presentation by Arne Henden. Okay, I see. And we'll record that separately for public posting, and then we'll record separately the business meeting. It will be in the news. Steve ran, public observing, education outreach committee, finance report, and other open business or member discussion. I am very, very pleased to introduce Arne Henden, the past director of the AAVSO and Legacy Fellow, AAS. On his, actually, let me just pull this up and maybe I can't read it. If you look at the calendar, Arne has impressive credentials in the field of science and astronomy. And I am very privileged and pleased to turn this over to Arne. Arne, I'm going to stop my share and let you share. And somewhere.
Okay, so are we there?
Yes.
Okay.
I don't see your screen. Actually, I
Yeah,
do.
we see his screen. We see
You
his
do?
screen.
All right.
Yep.
We do, yeah.
Good.
Yeah, so Joe asked me to give a talk here, somewhat similar to one that I gave for the amateur telescope makers of Boston. There they have a new telescope facility which has a 17-inch plane wave, and so I was giving them some ideas as to what they could do with that telescope. This one's going to be a little bit more general, and we'll be talking about some very easy ways to use a telescope and actually get scientific measures, all the way up to some of the more fancy ways. And in my career as a professional astronomer, I've used a lot of very large telescopes, building instruments, putting them on, testing them out, what have you. But my guess is that I've looked through a big telescope maybe 5 times in my life with my eye. It's all done with instruments, all done with computers. And so when I retired to New Hampshire, I decided to buy a house that Mario Mata used to own. And it had in the backyard a 32-inch telescope. So I was very happy to have that, to be able to do some visual observing as a retired and from professional, now amateur astronomer. So the big building on the right-hand side is the dome for the 32-inch. The two other structures, the one in the middle, the white one in the middle, contains two telescopes that are fully automatic. And then there's a Boltwood cloud sensor next to that. And then the final one to the left is an empty enclosure right now. And we're going to be putting a daylight telescope in there to actually monitor some stars during the daytime. So this is the inside of the 32-inch. It's a 32-inch f4 fork mounted. It is not automated at this time. It's just fully visual instrument. We are in the process of doing complete refurbishment of this telescope and making it a automated telescope so that I can use it when I want to visually, and then on other nights we can use it in a robotic fashion. And then inside one of the that middle enclosure, here's what you see. It's a Paramount ME with twin telescopes on it, a 12-inch f4 wide field, and then a Takahashi E180. And those are both imaging telescopes. The 12-inch has a QHY 600, and the little yellow telescope has a CMOS ZWO ASI 183 camera on it. Gives you about a 1 by 1.5 degree field of view. And again, that's fully robotic. It would be observing tonight, except I think the winds are a little bit too strong. And so I've canceled its program. It'll go on again tomorrow. So can you do science with small telescopes? Things of this sort. The 7-inch telescope there, the 12-inch, the Dobsonian you have in your backyard. And it's a question, if you want to do true science, it's a question of parameter space. So for example, people who have 4-meter and 8-meter telescopes just don't look at the bright stars. It's very seldom that they do. And so they're being ignored. Transient objects require immediate attention, and it may be daytime at the professional observatory, whereas it's night for somebody with a telescope in their backyard. So these are things like Novi, supernovae, gravitational wave optical counterparts, anything that increases in brightness very quickly. You can also do long-term monitoring. So you look at a long-term variable, a Mira star or something like that. And these things may have a year or 2 or 3 year pulsation cycle. And a typical graduate student with a 4-year lifespan in school just can't monitor one of these things and be able to do anything of substantial value. Even the professional surveys have lifetimes that are maybe a decade in length, and there are stars that require far longer than this to be able to monitor them. So amateurs are really excellent for doing that kind of activity. There are unusual observation modes. I mentioned that one of these telescopes in my backyard is going to be doing daytime observations of bright stars. Or you may have a really wide field, 2 by 3 degree field of view or something like that, that you use for your deep sky photography, but it does really well for observing large numbers of variable stars at the same time. And it's hard to do that professionally. And then, of course, spectroscopy is a more advanced technique, but there are very few amateur spectroscopists out there. And with the new surveys that are coming online, the Rubin telescope, LSST, is going to need a tremendous number of stars followed up, and spectroscopy is a great way to do that. So what I'd like to talk about are sort of 5 areas where you can contribute to science, and they're listed here. I'll go through them as we progress in the talk. And in the context of an easy or cheap solution, what you can do with that kind of a setup, more moderate, somebody has a DSLR and is used to doing deep sky imaging, well, then there's plenty of projects that they can do. And if you really get serious about it, then you may go with a monochrome CMOS camera, add some photometric filters or a diffraction grating, or even put a spectrograph on your telescope. As long as it's a go-to tracking telescope, you can do any of those things. And the thing to remember on this is that you are amateurs, which means you have a love of the sky. And so have fun. So, you know, pick stars or objects that are interesting to you, and study them and just see what you get. You don't have, for scientific observations, you don't have to be a scientist. You don't have to have a degree and considerable training and research interests. You just have to be able to measure the brightness of the star and turn it into a repository like the AVSO. So visual observations are fine to watch the changes of many stars. And again, if you want to get fancier equipment, well, then you get even better and better results. And those are more and more likely to be used by the professional community. Here are two really good books that if you get a chance to look at them in the library or buy a copy through Amazon or something, I highly recommend them. Jim Kaler does an excellent job of writing, and he's picked out a bunch of stars that are just really cool and fun to look at, just to read about, and also, you know, to look at with your telescope if you have the opportunity. So let's look at visual observing, which is the easiest method of doing a scientific observation with your telescope. There's lots of bright objects that you can see. Many of them are prototypes of variable star classes, and many of them actually haven't been looked at by the professional communities for 100 years. You look at Algol or something like that. You look at Betelgeuse, which only recently gained a lot of professional interest. But those stars are easily accessible by you with, you know, naked eye or with a small telescope or even a pair of binoculars. You can do science with them. For example, transient objects, looking at Novi. You hear about a nova that was observed by somebody in Europe. You can immediately get onto that object, and it may still be daylight in Pasadena or at Kitt Peak, and they won't be able to take any observations. So you get to get on it first. If you want to look at variable stars, the best place to go is the AVSO website. It's got a ton of material on it. It's kind of difficult to look through, but if you just start from the front page, I'll show you that in a second. It has links to get you to tutorials and a few videos and lots of supporting material like generating finding charts and what have you. And so it's a good place to start. And if you become a member of the AVSO, they also have a mentoring program so that if you want to learn how to do visual observing or learn how to use your one-shot color camera and do photometry of variable stars, they have mentors that will help you do that. And so what I want to show you for visual observing are some slides that are from this 10-star tutorial, which is linked from the homepage. So here's the homepage, and if you, let me get the right one here. If you go up here to this Getting Started link up at the top of the page and pull that down, you will get a number of links that will get you into tutorials and subsequently this 10-star tutorial. And in the 10-star tutorial are a bunch of charts that you can use to look at the stars. The 10-star tutorial is primarily a naked eye tutorial. And so all the stars in there as examples, the 10 stars are all easy to get to with your eyes. And there's one for the north and there's one for the south. So the one from the north is what you would want. And for example, this chart here has two, Alpha Ori or Betelgeuse and then Eta Gem. And in addition to that, for the 10-star tutorial, they actually show you the outlines of the constellations. They do everything in a negative image. So the stars are black, the sky is white. That makes it easy for you to print out and make notes on the charts as you see fit. And then you'll see a number of stars here that have numbers beside them, like a 1-6 and a 1-9 and a 4-1. These are stars where it's the magnitude of the star as a reference star, but with the decimal point removed. So this is magnitude 1.6, magnitude 1.9, magnitude 4.1. And the reason the decimal point is removed is because that looks like a star on these kinds of charts. So you just drop it out. So a chart like this shows you that there are two easy stars to get to. Alpha Ori is kind of an irregular variable. Eta Gem is a sort of semi-regular variable. It also is an eclipsing variable, so it has a number of different variability modes that make it interesting. But let's go down here and look at Betelgeuse, since that was in the news just this past year. And let's look at how you would make an observation visually of Betelgeuse. At the bottom of Orion are these two stars, Rigel, which is listed with 0.1, so it has a magnitude of 0.1. And the other star in Orion has a magnitude of 2.1. And so if you look at Betelgeuse in this chart and look at its brightness compared to these two comparison stars, you can see that it's basically the same brightness as Rigel in this particular example. And so if you were making a measurement of the star, you would say that it has a magnitude of 0.1. You would note the time, and that's the report that you would give to the AVSO. Now, what about this chart? Now Betelgeuse is faded. And if you look at it, it's between the magnitudes of the two comparison stars. And when they're so widely separated, two magnitudes in this case, you sort of have to interpolate and just take a rough guess as to what magnitude you think the Betelgeuse is at. And let's say that it's sort of halfway in between. Maybe it's a little closer to the 2.1, so maybe give it a magnitude of 1.5. And that's the kind of number that you would then report to the AVSO. And then here's the final example of that. You can see now that it's basically the brightness of the 2.1, maybe a little bit fainter. The trouble is, in this field of view that we've shown here, you don't have a 3.1 or a 4.1 star. So you don't have that second one that you need to interpolate. So you would either report it as, say, magnitude 2.1, or if you were used to this kind of measurement, you might report it as something a little bit fainter, say a 2.4 or something like that. So it's up to you as to exactly how you would report it in a case like this. So the hard part on visual observing is primarily locating the field. You don't have nice crosshairs on the variable star. You don't have magnitude labels on the comp stars. And so you have to either do star hopping and find the appropriate field, or you have to have a go-to telescope that will point you to the appropriate field. Then you have to locate the target, and you have to locate what sequence or comparison stars the AVSO, for example, has produced for that particular variable star. And then you can start taking your measurement. So it's not as easy as taking a picture of the field where you can then look at it on your computer screen in the daytime and figure things out, or use your plate solving program to be able to get an accurate position of a star. But it doesn't require any extra work. It just requires a little bit of common sense on your part. So one of these stars, for example, is Algol. And like I said, it really hasn't been looked at. If you go back in the literature, there are only a couple of photometric light curves of Algol. And it's really surprising because here it is, a star that's, second magnitude most of the time, goes down to magnitude 3.3 at its minimum. And the eclipse for these stars, these are Algol type eclipsing variables named after Algol, lasts about 8 hours. So the trick here is to find out when an eclipse is going to take place and whether it's going to be in your sky at night. And so here are two possibilities. There's one coming up in 20th of January, UT. So that would be the 19th local time. So it starts right at midnight UT and goes to 9 hours or something like that. So it you can watch the beginning of the eclipse, since Algol is now sort of in the western sky at dark. And the next one is the next eclipse, which is 3 days later. And you can see that the time has moved a little bit. And there you can watch the end of the eclipse. And so if you've never watched a variable star visually, this is a good candidate to do, because it really does change in brightness. You can just sit there and watch it as it either fades or increases in brightness. And there's the finding chart for Algol. You can see it's really easy in Perseus. In the same field here is gamma Cas, which is another nice variable. And this is the kind of light curve that you would be able to generate with your eyes. You can see that there's a horizontal structure, and that's because generally you report your magnitudes to the nearest tenth of a magnitude, and that's a tenth of a magnitude from that point to that point. So the guy interpolated, that's the best that he could tell, is whether it was magnitude 2.1 or magnitude 2.2, and then reported the appropriate value. And you can see the eclipses then when they occur. So this is something that's really easy to do. Anyone can do it. Cataclysmic variables, where you have a white dwarf and a red dwarf donor star, where the matter from the red dwarf is either falling directly onto the white dwarf or into what's called an accretion disk. These guys tend to flicker as that accretion takes place. And then every now and then, when enough matter has fallen onto the white dwarf or its accretion disk, it will actually flare up and increase in brightness. And here's an example of that. This is UGem, which is another variable star in the Geminorum. And the variable itself is this little faint star right there. And you can see in the second image that it has increased dramatically in brightness. And if you're doing this visually, quite often the cataclysmic variable is sitting down at 15th, 16th, 17th magnitude, and you can't see it normally. But when it goes into outburst, all of a sudden the star appears in your field of view. So it's an easy sort of binary, it's there or it's not there. And so that's a easy kind of target to go for. And it's kind of fun seeing that star all of a sudden appear. And it does it in a semi-regular but really random fashion. It may be something where it goes into outburst every 60 days or something like that. But on one cycle, it might be 55 days, and the next one, it might be 70 days. And so you really don't know when it's exactly going to occur. So again, to do visual observing, I think a go-to mount is really nice, but not essential. You can look for patterns and follow it down and identify your star. Typically, with your eye, if you have a good sequence, you can do better than 2/10 of a magnitude. But if you have stars that are sort of half a magnitude or a magnitude apart, you'd be lucky to do 2/10 of a magnitude interpolated between those two comparison stars. You have to be patient if you want to do light curves. So if you're looking at a Myra variable, which may have a period of 500 days, that means that you have to watch it for 500 days for it to go through its entire cycle. So it's a year and a half of your observing. You don't have to do it every night, maybe every week or something like that. You get a data point, but it's not something where you get instant gratification. So in general, for visual observing, I kind of pick 5th magnitude. Anything brighter than 5th magnitude is good for naked eye observing. You can go fainter than that, especially in a dark sky, but it's really hard to start picking out the variable itself when you get close to your limit. Binoculars sort of 5 to 10, and then telescopes basically anything fainter than that. The AVSO also has what are called choice courses. So if you belong to the AVSO, you can take one of those courses and it will teach you how to do visual observing, how to create a program of stars that are of interest to you that you want to observe. And the same thing goes for CCD and DSLR observing. So for people who have a DSLR or a one-shot color camera, you may be using it for doing deep sky photography, looking at M42, looking at M38, looking at one of the nice big galaxies that gain a lot of press. And the neat thing about it is you get an image, which means that you now have a permanent record of what you were looking at. You get 3 band passes simultaneously with the red, green, and blue channels. And so you can actually do a multicolor photometry of objects in that field of view. So this may be photometry of stars. It may be looking at extended structure of some object like a comet. You can do some really neat image processing of the coma of comets. But if you want to do photometry with one of your color images, please, the most important, most critical thing is don't overprocess your image. If you are a deep sky photographer, you know all about the fun filters and gradient removal tools and everything else that you can do to really make that image pop. Don't do it if you want to do photometry. Just basically do dark subtraction and flat fielding and call it good. And then you need software that will give you photometry, aperture photometry, as it's called, of stars within the field. You can use the VPhot program that the AVSO has available for its members, or you could use something like your acquisition program, MaximDL. But I would rather you use those than something like PixInsight, which is a really great color imaging tool, but is kind of a poor photometry tool. Here's an example of the kind of pictures that you've seen elsewhere. This is Comet Neowise from last year. And the area where you can really do some interesting science is actually the nucleus or a coma of the comet, not necessarily the tails. The tails require really wide field cameras and some interesting image processing in order to look at the tail and not worry about the streaks on the stars or streaks on the comet itself. But the coma is really easy to deal with. There's some interesting techniques that you can do to pull out the jet structure from the coma and to be able to watch the rotation of the nucleus of the comet as it approaches the sun. So that picture you saw there was from Gerald Rehman, who is a really nice amateur who does his imaging in Namibia. And there are some comet forums in space.com and Cloudy Nights to get you some access to people who are doing that and to learn about it. And again, there's a nice book down there by John Brandt and Robert Chapman on the introduction to comets and what value they have as in a scientific way. Asteroids, if you have an imaging camera, is another thing. It seems like every time you take a deep sky photograph, there's an asteroid in it. And there's over 1 million of them that are known, primarily from these near-Earth asteroid surveys. You will not be able to discover very many asteroids. If you see one in your image, most likely it's been seen many times before. They know its orbit, it's already identified. Don't try to get into the discovery parameter space, because you won't be very happy doing that anymore. There's too many surveys that are out there. But there's a lot of science that can be done on individual asteroids. The one is looking at the rotation rates of the asteroid. And if you get light curves of the asteroid over multiple phase angles, you can actually pull out the shape of the asteroid. You can get the size of the asteroid by looking at stellar and lunar occultations, primarily stellar occultations. There requires kind of specialized equipment. You need something that gives you a very high frame rate, such as a video camera. And also a piece of equipment that will give you a timestamp on those images so that you have a good idea as to when the dip in brightness takes place. IOTA is a good occultation group to look into. And then again, they have forums on the typical sites. Here's an example of Eros, a near-Earth asteroid. And you can see that these asteroids tend to be small. They tend to be very irregular in shape. And because of that, they have a variation in brightness due to how much of the surface is reflecting in your direction at any given time. And so you can actually watch the variation in brightness. That gives you the rotation period. It also, like I said, if you look at it at multiple phase angles, you can get the shape parameters, so you can actually get a shape out of this as well. Deconvolve it. It's really pretty cool what you can do. So let me, probably from here on out, I'm going to be talking about variable stars. And like I said, there are about 2 million of these that are known and cataloged at the current time. And if you want to see the whole list of catalogs and search it, it's this variable star index, VSX, that's available on the AVSO website. Now, all stars vary in brightness if you look at them over astronomical timescales. But variables are the ones that vary within a human time frame, so minutes to days to weeks, that kind of thing. And that's the 2 million that are measured or cataloged in VSX. And they include periodic variables where it's an eclipsing variable due to 2 stars passing in front of one another, or it could be a single star like a pulsating variable, a Cepheid or an RL-IRA star. This is a means of measuring the structure of these stars in a remote fashion, since you'll never be able to go to them yourself, to understand both the system geometry, in the case of an eclipsing variable, or the structure, the interior structure of the star by using the variations in brightness that you measure along with models of stellar interiors. Now, you don't have to do the modeling. All you have to do is provide the observations, but you can do the modeling. Those codes exist. So the light curves themselves contain tons of information. You can do it in multicolor. So say you're doing your one-shot camera images, that gives you 3 colors. Those differences in wavelength give you information about the temperature of the star. And it gives you information about the temperature of the star as a function of where it is in its light curve. And the light curve itself, if you measure it today and then measure it again in 5 or 6 years or something like that, you can often see a change in the period. This is especially true with the pulsating variables because their structure changes as a function of time, and so does their period. And then the other thing to note is that for exoplanets, the host stars themselves often are variable. And if it's like, for instance, a flare star, the variability of the host star can impact the habitable zone around the planet. So it may be in a nice, liquid water area, but if it has strong flares, well, then it may just zap any kind of life that might develop there. So even the exoplanet surveys and the people that are trying to look at the planets themselves, they have to understand the host star. And so the more information they have, the better. And they often go to the amateur community to get that. there's that 10-star training tutorial that I was telling you about. And if you're doing, imaging, there's a number of guides on the website, and it tells you how to actually take those kinds of observations. You don't have to choose your own stars. There's a list of legacy stars for you to monitor. There's also alert notices where somebody's observing with HST and they need to have ground-based support to find out what the photometric behavior is of a particular star before HST starts to observe it. That's certainly the case in a couple programs that are going on right now. And you can also work one-on-one with a professional astronomer, or you can analyze the stars on your own if you decide to go that route, and perhaps write a paper or give a talk at one of the amateur meetings. Here's one of the alert notices that went out in December. This is B-PER is a triple star system that eclipses. So you can either get a eclipse of the inner pair of stars, or you can get an eclipse caused by the wider tertiary member of the system. And so this particular researcher wanted observations by the community to be sure that the eclipse of the star, that happens every 2 or 3 years, would be carefully covered. So, like I said, it's a kind of a parameter space issue. Just like with asteroids, studying run-of-the-mill variables or trying to discover variable stars is really pretty rare, because there's a lot of surveys that are out there that take that kind of data. And so you wouldn't be contributing much. On the other hand, some of these stars are really cool and really nice to look at. And so for classrooms or for just your own education, I think they're wonderful to do. And more data never hurts on any of these stars, because you can never know what's going to happen. The main science areas, though, are for transients, like I said, like Novi and Supernovae, doing multicolor photometry. This is essentially low resolution spectroscopy, sort of a resolution of 5 when you think of the 5 photometric filters that cross the wavelength regime that a CCD camera or a CMOS camera covers. And then again, long-term monitoring, very bright stars like we were talking before. Crowded fields is another area where the surveys start to fail, because in order to cover the entire sky every night, they have to have very large pixels. That means they don't have the kind of resolution that you would need in order to identify a variable star amongst its crowding neighbors. And for anything that requires time series work, so the eclipse of a cataclysmic variable, which might take place in 10 or 15 minutes, a wide field survey that covers the entire sky once per night is not going to be suitable for doing that kind of research. And then there's a whole bunch of unique variables that are fun to follow with more detailed monitoring than the surveys could do. Here's a pulsating variable. Typically, you can see that it changes color as a function of its size and pulsation. And this is the kind of light curve that you get for that kind of a star. This particular one is W Virginis, which is a prototype of population 2 or older metal core stars. And you can see that even though you have 4 increases in brightness on this graph, it actually only covers 2 cycles of the star, because you can see that the variation in this cycle is different than the variation in that cycle, and the minimums are different between the 2 cycles, but then repeat on that 2 cycle thing. So 2 of these bumps are included in a single cycle of variation of this particular star. This is about 34-day period if you look at the 2 cycles. And so it's something that you can cover pretty easily over just a few months of observation. Now, the harder observing of variable stars and other things in the universe require that you use a monochrome camera, and then you put standard photometric filters in front of your detector. And that means that you have to have a filter wheel, you have to have photometric filters, which are a little more expensive than your typical narrowband filters. And because it's a monochrome camera, you get 1 bandpass at a time. So it takes longer to go through this. The usual photometric filters that are used for studying variable stars are what are called Johnson-Cousins filters. BVRI, where it's blue, visual, red, and infrared are the reasons that are named that way. And if you use those filters, you can still do your deep sky photography. You just use BVR instead of RGB, and you can do it. It's a little bit less sensitive because the band passes are a little narrower, but you can still do very good pretty picture work with photometric filters. These filters and a monochrome camera give you much better precision of your photometry. And because they're all standard, then as you submit your data to the database, your results can be compared with others because they're going to be using the same standard filters. Here's an example of what you can do in sort of tricolor photometry imagery. This is the Calabash Nebula, which is right next to M46. M46 is well known because it has a really cool planetary nebula in it. And so it's a fun open cluster to image. But if you look just a little bit to the east of it, there's this thing. And this was taken with my previous job's US Naval Observatory 1-meter telescope in BV and I. And you can see that this is a very red object. And in particular, it's a bipolar nebula. And right in the center, you see sort of a darker area. And this is a circumstellar ring of material that surrounds a long period variable. It actually looks like a Myra variable. And if you look at it with your telescope, primarily you see this area down here, which is a part of a reflection of the light of the star. And so this is what varies, it's this thing here. And if you do photometry of this field, that's the thing that you're probably going to be doing photometry of, not the fainter extremes of this particular object. If you look at this in the near infrared, this was also at USNO, but with the 61-inch or 1.55 meter telescope. This is what it looks like in the infrared. So you can start seeing that, you know, there's a lot of really cool structure in this particular object. You can pick up some of this stuff if you have really good seeing in the optical, but it's hard to do. And now you can see the reflection off of this southern part of the nebula is still very prominent, but you still can't see the central star. To see the central star, you have to go basically out to about 5 microns before the dust clears enough that you can actually see the star itself. But when you do, then you actually get a time difference because the star is pulsating in here, and then sometime later, that light reaches the reflection nebula and then gets to you. So there's a time delay. And so you can actually see a time delay between the variation of the star itself and the variation of the reflection off of the nebula. So that's kind of cool, and you can actually determine distances to various structures and all this kind of stuff. So it's a fun thing to think about, at least. This is the variation for QX pup itself, and you can see that it's kind of a really nice long period variable. It has a period of about 900 days, if I remember right. And this is just off of that southern part of the nebula. Tavstar is another fun one. This is from the Kepler field, so it's up near Cygnus and Lyra. And you can see it's kind of just a nondescript star in the middle of a bunch of other stars. Really nothing spectacular about it if you just do a single image. But if you do a light curve of it, this is the kind of thing that you see, is that the star has kind of a quiet or quiescent magnitude sitting up here. And then every so often it dips down in brightness. And this was a really contentious object. It's still up for discussion as to what's causing the dips. But there was a number of science.com articles and things like that about, maybe it's a Dyson sphere, and you pick your exotic thing that can cause these kinds of dips, and somebody has written an article about it. So just monitoring it in long term gives you a chance to keep looking for eclipses, or waiting for all this structure that's in front of the star to fade away, or whatever, and so that's what a lot of amateurs are doing today. All right, so wrapping up here a little bit, transient objects you can do with any of the methods that I mentioned before, visual, DSLR, or a photometric system. Flare stars are a common target. The trouble is with flare stars is that, except for a couple examples, they flare and then they may not flare again for another month. And the flare itself only lasts for like 15 minutes. And so the chances that you're going to see a flare are pretty slim. And that's why most of the surveys don't see the flares. You just have to sit there and monitor a single star. Novi, supernovae, gamma ray burst optical afterglows, gravitational wave events, all these neat things that are transient just aren't covered very well by the surveys. Perfect objects for amateurs. An example of this is GK Per. It's a Nova Per 1901. It got up to about 0th magnitude, so as bright as Vega. And this is a relatively recent image of it. And you can see that here's the star itself in the center, and you can see the matter that has been ejected from one of the outbursts from that star. If you do this over a number of years, you can actually watch each one of these globs of material as they move outward. And you can determine not only a velocity of expansion, but you can also extrapolate that back and see what date those particular blobs were ejected from the star. This is the light curve from GK Per. You can see that back in 1901, it reached a magnitude of 0. It faded pretty quickly over a period of about a year or so. And then it slowly faded down to a magnitude of about 13, and then it's been pretty steady ever since then. And notice that once it faded to sort of its quiescent level, then all of a sudden you started to see smaller outbursts from the star. Now on this plot, a couple of interesting things. The first is you see some colored dots over here on the right-hand side. This is the advent of digital photometry for this particular star. So this is sort of in the 1980s, 1990s. Therefore, from there forward, you have both visual and CCD, CMOS photometry of the star. And the second thing is that all the visual measurements are these open circles, and they just get black because there's just so many of them in through here. The triangles are observations where somebody looked at the field and they couldn't see the star, probably because they're dealing with a small telescope. Here's 11th magnitude or something. They couldn't see it even though it was sitting down here at 13th magnitude at the time. So these are upper limits, what are called fainter than. This is a more recent past decade for GK Per, and now you can see these individual outbursts go from magnitude 13 to magnitude 9.5 or something. So that's a 4 magnitude increase in brightness. Pretty nice. But they don't happen very often. They're not very regular. And you don't know when it's going to go and do another one of those 0th magnitude outbursts. So it's one of those things where you just keep watching it, waiting for it. There's even a whole series of stars that astronomers have picked out in our galaxy where they think they may go supernova someday in the future, and maybe in the near future. And so they have a list of these things, and they just want amateurs to continually to monitor those stars. You don't know whether it's going to go off next week, or, you know, your grandson will be the one who detects the outburst. But we're waiting for that next big supernova in our galaxy. Here's another one of these cataclysmic variables. You can see this one has much more frequent outbursts, and even the quiescent level tends to shift around. So they do a lot of interesting things, and astronomers continually try to come up with theories as to why the variation is what it is. The other neat thing about Novi is that they tend to be in very pretty fields. Quite often they're in the Milky Way plane, and so you get lots of pretty stars around. And in addition, you get quite often a nice red nova star that's sitting in the field as well. So they're fun to look at just with a standard deep sky photography. And you can still take those images and then process them and give photometry out the other end. Here's a nova, 10 years of a nova. See that goes up bright, gets fainter over a long period of time, but it's continually changing in brightness. Here is a whole bunch of novae, and you can see that while some of them are pretty similar in shape, others are very different in shape, but they're still classified as novae. So looking at one doesn't mean that you've now looked at a nova and you don't have to look at them again. Each one is going to be a little different. And then supernovae are also a neat thing to look at. This is M101 with the supernova that occurred in 2011. Now, you may think that you've taken, that everybody's taken an image of M101. So why should you take another one? Well, you're the only one who happens to have a supernova in your particular image. So you have a unique representation for M101 that somebody who was imaging with a big telescope 10 years ago doesn't have. So you have something that is really unique about your image. And then again, you can follow the supernovas as it fades. Supernovae take more like a year to fade. And so you can watch them for a long time usually, especially in a nearby galaxy like M101. Here's the light curve from it with different filters of information. These are the 4 photometric filters, BVRI, that I was mentioning before. You can see that the variation is very different depending on the wavelength that you're looking at. Exoplanet transits is kind of the last thing. They're like an eclipsing variable, except that it's a dark object that's passing in front of the star. And the planets are small, so the decrease in brightness due to the dark object is equally small. Something like Jupiter seen from some distant star, looking back at our star, would only cause about 1/100th of the magnitude dip in brightness across the face of our star. So it's a very small dip. Takes a lot of skill to be able to do this, though there are a number of amateurs who are actually monitoring exoplanet transits, and as a matter of fact are helping the test satellite through their follow-up observing program. This is the kind of a typical dip in brightness for one of these stars with a extremely good telescope. This is really hard to do from the ground at this kind of precision. I've only seen a couple, but the photometry in a time series is going to be constant at the beginning and at the end. And then as the dark object goes across the face of the star, you have what's called limb darkening of the star. Hits the center of the face of the star, limb darkening on the other side, and then exits the star. And so you can actually get not only timing on an exoplanet transit so that you can get the orbit, but you can also tell something about the star itself. And there's an exoplanet section at the AVSO. So you can go there and see what what resources they have, as well as what kind of campaigns and targets that they will suggest for you to examine. And then finally, I want to end up here with this object. Some of you might actually have tried to do this. This is JWST as it was heading out to its orbit. While it was going out for the first day or two, it wasn't all that bright, but once they unfurled the sun shield, it increased in brightness to about 13th magnitude, and you could actually do imaging of this object as it headed across some really pretty star fields. I think you can still do that with JWST today. So you can do it with asteroids. You can also do it with satellites like this. Fun stuff. This actually ended up being an astronomy picture of the day. So in summary, professional surveys have their limits. And so with small telescopes, you can still contribute science. You can also just have fun with variable stars and other objects in the universe. There's plenty of scientific opportunities, all the way from just contributing data to doing your own analysis of things. It's great for student participation, for example. There are many organizations that have excellent resources to train you and to give you guidance. And I think it's just a fun thing to do. And, you know, I started out as an amateur. I'm back to an amateur. And I'm still doing a lot of this stuff just because I'm enjoying playing around with these stars. So again, here's my contact email. I'm available anytime that somebody wants to talk to me. And the AVSO has that great website. I'm hoping to open up the 32-inch this year for some public observing, and maybe I'll see if the New Hampshire Astronomical Society wants to come out. But I am a member. I am officially a member now. And so anything that I can do to help out, I'd be happy to do so. So thanks. And I will stop sharing.
Arne, that was great. I guess I will share. See, I will share. Let's see this. Share. Let's see. So that was a fantastic speech and presentation, and I am going to check out a little bit more about this. Any questions for Arne?
I have a question. You're talking about transient events. And, you know, one thing I've noticed in my long observing time, since I was just a teenager, is that sometimes I'll notice a blip in the sky, very, very small transient. Now, originally these were before satellites became numerous, and nowadays, you get tumbling satellites and so forth that make it look like you have a transient event going on. But I don't know if anybody, I mean, I'm thinking again of gamma ray bursts and that kind of thing that would be a visual component to that. Is there anybody who's doing any research in a visual kind of way to, look for those kinds of transient events?
The problem with those transient events is that there's no permanent record of it. And so you didn't take a picture of that particular area of the sky, so they can't pinpoint it, and they can't necessarily show that it's one type of event or another. But there's certainly possibilities as to what that kind of thing could be. An example is a head-on meteor. I've seen those myself, looking at the Geminid meteor shower back when I used to live in New Mexico. And, like you said, gamma ray bursts, they are beamed events. And so there are theories that it can be, a gamma ray burst can be seen in the optical, but not necessarily seen in the gamma ray region, and so not detected by the satellites. So there are, a number of things that are really transient that might be the case, but for a particular event, I can't say. It's almost like dealing with UFOs. You just really need that permanent record in order to be able to even have a chance at identifying it. But
Yeah,
I
I'm
certainly
wondering
believe
if
it.
somebody had like an all sky camera going that
Yeah.
might pick something up like that.
That's actually a good point. There are a number of all sky cameras because there's, a meteor network, for example, which is devoted to looking at the sky with all sky cameras, and then if two cameras pick it up, then they can triangulate and actually get orbits of the meteors and things like that. And so there are people who are looking at the sky all the time with that kind of a system now, that when you were younger, wasn't the case. So if you saw some sort of transient event now, there's a possibility that there is a permanent record of it if there happened to be one of these all sky cameras close to you.
All right, thanks.
Any other questions for Arne?
This is Rick. I have a question.
Rick?
Hey, Arnie, I'm sure you're aware of this unistellar EV scope and the SETI Institute's partnership with Unistellar to create a citizen science network. They've been doing some asteroid work. They've been doing some exoplanet transits, things of that sort. There's about 1,000 amateurs around the world now who have these things. I'm just wondering if you think that's going to make a big impact, or if you think it's just a sort of like a passing fad almost.
Yeah, it's hard to say. They are producing standard FITS images and things like that now. I think on their website. It takes a while before you can download it, but it's certainly a telescope and a digital detector, and it's certainly capable of doing true science with something like that. And once you start having this crowdsourcing where you have thousands of these things around, you can get some really neat things. Asteroid occultation event in which you've got 50 chords across the face of the asteroid. And I think it's a useful thing. I was thinking way back when that what would have been nice was the fact that you have all the cell phones that have backside illuminated CMOS sensors in them, and some of them are extremely low light level systems. You can certainly take pictures of the sky with those, and those are another camera that's available to a large community that could also do real science if you crowdsourced it. But I think the Unistellar is a decent system. It's just like $3,000 a coffee or something. And for your own personal observatory, that $3,000 is probably better spent in getting the CMOS camera and a few filters than buying a Unistellar and setting it up in your backyard. But if for public events, it's the way to go, I think.
Thanks.
Any other questions?
No, but I just want to say I found this presentation really helpful, because when I go out to observe, I'm bouncing around looking at Messier objects, but I like the idea of focusing on something specific and having like a purpose to it. So that this is exactly why I joined the astronomy club. It's because to get this kind of thing going. So very helpful.
Yeah, and the other thing is that you realize that if you look at some of the Messier objects, especially if you're using a camera, so say you're doing a globular cluster or something like that, there are hundreds of variable stars in that globular cluster. And, if you're sitting there for 10 hours trying to get the ultimate image of M15 or something like that, this is a perfect opportunity to sit there and now look at each individual image, measure those stars, and you get light curves of 100 different stars all simultaneously. So for imaging, it really opens things up because of the multiplexing advantage. But for somebody who's just doing visual observing and going from one object to another, there are also, bright, interesting stars nearby that are fun to look at. And, you measure them as part of your program.
Yep.
Any other questions? Arne, thank you. Thank you very much. I am glad to start the year with an excellent presentation, and I am very pleased. At this point, I am going to stop the recording and turn it over to our business meeting as soon as I can find the switch to stop the recording. Here we go.